Hello, my name is Madison Whiteman, and I am going to be going over the solutions for our midterm exam. So, beginning with question 1, this asked us for the power grid and its services. It asked us first to define with as much detail as possible what is frequency regulation. And so for this specific section, the focus was on the power grid and its services. And a lot of that information we're going to see in lecture 8 on storage, as well as some supplementation from lectures 3, 4, and 5, especially when we're talking here about frequency regulation. So frequency regulation helps to balance momentary differences between electricity demand and supply within the transmission grid. This is often in order to help maintain interconnection frequencies close to 60 hertz. For example, with the swing equation, this is used to determine the deviance from that 60 hertz requirement for our grid. When the demand is greater than the supply, the frequency decreases. When the supply is greater than the demand, the frequency increases. So this regulation is really important in order for us to be able to have our grid running properly and to be meeting that demand and supply. Question 2 was define with as much detail as possible what are spinning reserves. And so spinning reserves is the unused dispatch generating capacity of online assistance that provides grid frequency management. This may be available to use during significant frequency disturbance, such as during an unexpected loss of generation capacity. This reserve ensures system operation and availability. Dispatch generators are those that can be turned on and off in order to meet immediate needs of the system. For load following, it supplies/discharges power or absorbs/charges power to compensate for load variations. This application is a power balancing application, also known as a form of ramp rate control. And so from what we can see, the next question that we have is, from the grid services listed above, which services can be provided by battery storage? And so all of these can be, battery storage can play a part in. So battery storage can replace spinning reserves and load following and can aid in frequency regulation. When the supply is larger than the demand, the battery storage can be in place to absorb the extra energy within the grid system. And then when the demand is greater than the supply, the battery storage can be in place in order to add power into the grid system. Battery storage is reliable because it is able to be digitally controlled to meet the demands of the system, and it's easier to manage than a mechanical system. So that's one of the reasons why battery storage is starting to be more of our go-to instead of the spinning reserves, just because it's a lot easier to maintain, and that digital control allows it to be very quick response to meeting the demands of the system. And so moving on to question 2, I know this one was a little bit harder. And so this one describes the aspects that impact PV efficiency. So it says to use the figure and list below to make sure that we describe each aspect of it. The figure depicts the solar spectrum at air mass 1.5 showing the impact of unusable energy by crystal silicon PV cells. And so for this one, this came a lot from chapter 4 and chapter 5. So first, for us to understand, especially with air mass, we need to talk about solar radiation. So as solar radiation makes its way to the Earth's surface, some of it is absorbed by various constituents in the atmosphere, giving the terrestrial spectrum this kind of irregular bumpy figure. The air mass ratio also contributes to this terrestrial spectrum. That is how much atmosphere the radiation has to pass through to reach the surface. This equation right here shows the variables. So H1 is the path through the atmosphere that with the sun directly overhead. H2 is the path length through the atmosphere to reach a spot on the surface. And and beta is the altitude of the angle of the sun. So this determines our air mass ratio. When air mass ratio is 1, that means that the sun is directly overhead. But as we can see here, what we are using an air mass ratio of 1.5. And so this is significant, not just because we chose random things, but this is significant because this is considered to be the average solar spectrum at the Earth's surface. And so as we can see here, kind of at the top, here, let me do this in orange. So here at the top, we can see that it labels something for us to be able to understand. And so what this tells us up here is that about 2% of the incoming solar energy is in the ultraviolet portion of the spectrum. About 45%, no, about 54%, my apologies. 54% is in the visible spectrum, and about 44% is in the near infrared spectrum. And so as the sunlight passes through more atmosphere, less energy arrives at the Earth's surface and the spectrum shifts toward longer wavelengths. So question 2 asks us to talk about the impact, or part 2 asks us to talk about the impact of a material's band gap and relationship to the wavelength. But I feel like responding to 3 about the conduction band would be more helpful before we get into discussing the band gap and the relationship to the wavelength. And so from what we can see here, I provided some diagrams from the book just for us to be able to understand a little bit more about the conduction band. So the conduction band is the band of electron orbitals that electrons can jump into from the valence band when excited. This energy, the energy needed to jump into the conduction band, is called band gap energy. And so this band gap right here, this is for metals. This conduction band is partially filled. And here, this one right here, this is empty. And so what has to happen is this is where the electrons go. They have to jump this forbidden, they have to jump from one band to the other. And so what they're trying to do is, in our circumstances, we have them trying to jump from this filled band into the conduction band. Okay. And so there are certain constraints on what can jump into that conduction band. This conduction band is where we're able to get this energy available. And so what's going to happen is, for our specific material, we have crystal silicon PV cells. And this is when we can start getting into the band gap, the material's band gap energy. So the band gap energy for silicon is 1.12 EV. And this means that an electron needs to acquire that much energy, specifically in this circumstance, from the sun to free itself from the electrostatic force that ties it to its own nucleus, and then jump into the conduction band. Any extra energy above 1.12 EV is dissipated as waste heat in the cell. And so this is going to play a key into the wavelength. So specifically for the PV cell we are looking at with silicon, the photons with a wavelength greater than 1.1 micrometer have an energy less than, wait one second. So the photons that have a wavelength greater than 1.1 have an energy that is less than 1.112 EV band gap needed to excite an electron. So these sizes right here, those are the photons with wavelengths that are too large to be able to have the energy to excite those electrons to jump over this forbidden gap into the conduction band. So it just heats itself. So that's where we get, from right here on these wavelengths, that's where we get this unavailable energy. That makes up for about 20.2%, as we can see. And so right here, what we're seeing is now we have this band gap length of this 1.1 micrometer. And so anything below it, that's what we're going to discuss next. And so for photons that have a wavelength shorter than that 1.1, they have more than enough energy to excite that electron to make that jump into the conduction band. And so what we're seeing here is that's where we have our energy available comes from these wavelengths less than 1.11 micrometers. But as we can see here, that is highlighted in green, there's still some unavailable energy. And so what we ask ourselves is, what are we seeing from that? Why is that happening? Shouldn't all of this energy be more than enough? But what we have to remember is that the constraints on it are that the energy has to be at 1.12 EV. So anything greater contributes to that unavailable energy. And so these constraints put on silicon's band gap limit the efficiency to just under about 50%. And additional constraints come from black body radiation losses and recombination losses. And so what these losses are is when cells get hot in the sun, their surfaces radiate energy proportional to the fourth power of their temperature. And this is about 7% loss. And that's what we're getting from this black body radiation. And then when we get into recombination losses, what happens is with those slow moving holes stacked up within the cell, it makes it more difficult for the electrons to pass through without falling into the holes. And so what this does is this accounts for about 10% more of these losses. And so what we're seeing here is that this all is heat, and then also right here, all of this unavailable energy can be accounted for by these wavelengths that are shorter that can't use all their energy and is equated into heat loss. And so this can answer for, that's the answer for here in exercise 2. As we get into exercise 3, we were asked to sketch and describe an idealized IV curve for a PV panel. Define in words and place in your sketch the following parameters. And so for V subscript OC, this is the open circuit voltage. And we can see that. I'm going to highlight this in orange. And so here we have our IV curve. And here, I forgot to label this, we have current. And here we have voltage. And what we want to remind ourselves is that power equals that current times voltage. And so right here, the first one asks us to do the V subscript OC. And from that, we can see right here at the end of this black line is the open circuit voltage. And what this is this is when the current is at 0. And this is the voltage when it is not connected to any load in the circuit. So current is 0, and this is what the voltage is in this open circuit. And its counterpart is, if we follow this black line as we go along, we then get to, I'm going to use green for this one, where we have our I subscript SC. And this is for the short circuit current. And this is the current through a circuit when the voltage is 0. So this means there's no resistance in this current. Okay, so we have these two opposites. And what happens is we have this IV curve that goes, and at some point, this big black dot that we have, I'm going to circle in yellow, this is called the maximum power point. And what this is the point on the IV curve at which there is the greatest power output. And as And so that's where we get this, not where we get it, but that's where we can see that the power is equal to the voltage times the current. And so what happens is there are specific values for voltage and for current at which this occurs. And that is what this subscript VMPP and the subscript I, or this I subscript MPP are. So this right here, the voltage MPP is the voltage at the maximum power point. So this is when this is the voltage at the greatest power output. And its counterpart is here at IMPP, which is the current at the maximum power point. So when power is at its greatest point. And so this next little kind of question to think about is, how would the sketch change if your radiance would double? From what we know about, I forgot to mention this earlier. So what we know from the short circuit current is that it's directly proportional to the solar flux. Therefore, if irradiance is doubled, this is directly proportional to solar flux, the short circuit current would be doubled. And so that's where we get this. It's written fairly faint. My apologies. This is where we get this new open circuit, this new short circuit current, and this new open circuit voltage, which would result in a new maximum power point right here, which then results in a new maximum power point current and a new maximum power point voltage. And so a lot of these concepts, we can go back and look at some of our earlier lectures, as well as I believe it's in chapters 4 and 5 that really go into talking about these PV cells. And if you need refreshers more on the currents, you can look into chapter 3 as well. Moving on, we now have this question, exercise 4, talks about wind energy. And so a lot of this is going to come from chapter 7. And so what this exercise asks us is to compare the amount of wind energy at 15 degrees Celsius and 1 atmosphere pressure that passes through 1 meter squared of cross-sectional area for the wind regimes listed below. Assume an air density of 1.225 kilograms over meters cubed. And so for situation 1, we have 10 hours of 6 meters per second winds. And so what we see here is that we have our energy for these 6 meters per second winds. And we have this equation right here, which we will be utilizing throughout this whole time. And what specifically this question we're going to focus on is going to be this concept of average wind speed. It's not always, we shouldn't always use average wind speed, and we're going to look into that right now. So from what we can see is here in this equation, we have 1/2 times the air density times the cross-sectional area times the velocity cubed times that delta t. And so we're going to plug in, most of it's going to look the same. So the first little bit's going to look the same. And so for this one, we have our 6 meters per second, and we're going to cube that and then times it by our 100 hours, and we get 13,230 watt hours. And so now we're going to look at our and that's our wind energy for regime 1. So now we're going to look at regime 2, which is at 50 hours at 2 meters per second winds, plus 50 hours at 10 meter per second winds. And this says here, average wind speed of 6 meters per second. So I'm going to change into purple now for us to look into this. And so for this, what we first want to do is we first want to evaluate that first 50 hours at 2 meters per second. And so what we have is we have our energy, we have our equation. We're going to plug it in that 2 meters per second, cube it, and then times it by that 50 hours, and we get a rather low number, 245 watt hours. What we're going to go into next we're going to look at that 50 hours at 10 meters per second. I'm going to change into yellow for this one. Let me change the size on this. And so what we see here is we have this energy for 10 meters per second we're trying to find. And so we're going to plug in all of our numbers as we did before. But air density isn't changing, neither is that cross-sectional area, but our velocity changes and our hours change. And here we see we get 30,625 watt hours, which is very significant. That is greater than doubled that of what we saw from this first one. So this is doubled even regime 1, and that's at about half the hours. And so from the two of them together, we get we have to add them together to be able to get this combination of the total hours, and we get 30,870 watt hours. And so why are they so drastically different? This number is significantly greater than that in regime 2. And what we want to look at is that for the second one, we didn't use this average speed. We had these two combinations. And so in question C, we have to ask ourselves, in this exercise, the average wind speed was the same for both regimes. So we need to explain why the wind energy in regime 1 was vastly different from that of the wind energy in regime 2. And from this, we see that the wind energy in regime 1 was less than the winds, was less because the winds are only blowing at a steady rate of 6 meters per second for 100 hours, while the combination of 2 meters per second and 10 meter per second winds produce more wind power. The higher wind speed at 10 meters per second for only 50 hours alone produced more than the wind power than that of 100 hours at 6 meters per second. And so for this, we want to make sure that we are focusing on not just doing an average, but that we are really that we're taking into account these speeds at different times. We can see here that this equation is dependent, the energy is dependent on that velocity. So as we have higher velocities, we're going to get a greater output. So even though we had a greater time distance in 1 than in regime 2, we did not have the same velocity, and that velocity really is going to impact how much energy we have. And so this kind of highlights the importance of not just using the average speed for all situations, but that we're really paying attention to the wind speeds that we have at different times and at not how many hours as well. That plays a huge factor into how much energy we're going to be able to produce. Moving on to question 6, this says for the equivalent circuit of a 0.03 meters squared PV cell shown in the figure, this reserve saturation current is I subscript 0 equals 4 raised to the negative 11th power A, and at an insulation of one sun, the short circuit current is 6.5 amps. At 25 degrees Celsius, calculate the following. This 25 is going to be very important because, as we can remember from our studying, especially in the earlier lectures, I believe lectures 3 through 5 specifically talk a lot about this PV cell. We remember that we have this equation for I, and at 25 degrees, we can simplify down a lot of these equations. And so that's where we're getting into, for the first part, it asks us to talk about the open circuit voltage. And so when we come here, we see that this, let me change into a different color. We see that this right here, this equation is, this is the open circuit voltage. And this equation is specifically for at 25 degrees Celsius. And so for that, we get that the open circuit voltage is 0.0257 times the natural log of the short circuit current divided by the reserve saturation current plus 1. And so when we plug in those values that we had, we get that the open circuit voltage is 0.663 volts. Moving on to the second one is, what is the load current and open output power when the output voltage is V equals 0.55 V? And so from that, we have this simplified equation again at 25 degrees Celsius. And from that, we get that the load current should equal the short circuit current minus the reserve saturation current times the XE raised to 338.9 times the voltage minus 1. And so what happens is we're going to plug in here, we're going to plug in that voltage that they gave us right up here. In orange, sorry, my apologies. So right up here, we have this voltage that they gave us. We're going to plug that into the V right here. And so from that, we get that the load current is 6.42 amps. Now we're going to go into what is output power. So we know that power is current times voltage. And so what we're going to do is we're going to take this load current and multiply it by the output voltage, and we get the power equals 3.53 watts. Now we are asked to find the efficiency of the cell at V equals 0.55 V, and we get that the output power, we get that efficiency is output power divided by input power. And so we get that the efficiency is that power from above put in, and this input power is the area times from up above. We had that insulation of 1 sun, and so you know that to be 0.03 meters squared times that 1 sun insulation of 1,000 watts over meters squared, and we get that the efficiency is 0.1177 or 11.77% efficiency. Exercise 6 asks us to upload our cheat sheet. I currently am unaware where mine is, so please refer back to the midterm for that cheat sheet. And with that, I thank you for your time and hope that this was helpful and that my answers were correct. Thank you for your time, and that is all.